Hello, my name is Mariana de Melo Antunes and I'm a mechanical engineering student at the Federal University of Itajubá. I'm here today to present a nonlinear inverse heat conduction technique to estimate thermal properties of metals. This work was developed in the Heat Transfer Laboratory from Unife by me, Rodrigo, Nicolas, and Professor Sandro. In this presentation, I'm going to introduce our objectives and motivations for this work, and I'm going to present our methods and results, and also our expectations for future work. So to begin with, I'm going to talk about our objectives, which is to estimate simultaneously and sequentially the thermal conductivity and the volumetric heat capacity as functions of temperature in a sample of 304 stainless steel. And we're motivated by the large applicability of metallic materials and its importance in society and engineering as well. The stainless steel, for example, can be found from home appliances to the automotive industry. And also, the metallic materials in general are useful in several manufacturing processes as the raw material or in the tools and in the accessories in this processes. So they're very important and very present in our lives. And something that we should always be concerned about is the effect of temperature in those materials. In engineering, there are many situations in which we have high temperature variations. And in order to apply these materials correctly and optimize our processes, we need to be able to understand the behavior of these materials under the most varied circumstances. And for this purpose, it's very important to know their thermal properties. But the problem is that these properties are very difficult to measure, especially in metallic materials, and they can't be obtained directly. They belong to what we call the inverse heat conduction problems. These problems require experimental data that, allied to optimization techniques, provides us the quantities that we're looking for. And over the years, many techniques have been developed in order to obtain those properties quickly and effectively. But many of them furnish just one property at a time, or have a high experimental cost, or they can't be applied in metallic materials. And in most of the cases, when we think about thermal properties estimation, we are led to parameter estimation. Which means that the property is considered to be constant. So many works don't consider the effect of temperature on the material. So in this work, we're going to apply a sequential technique based on the Gauss minimization method that provides us the values of the thermal properties for each time step of the experiment. So for every small change in temperature, we have a matching value for the thermal conductivity and a matching value for the volumetric heat capacity. So the properties can be written as functions of temperature. So for that, we have simulated this thermal model, which consists in a squared sample of 304 stainless steel with a resistive heater on the top surface and a thermocouple placed in the bottom. The model is one-dimensional and non-linear because the properties vary with temperature. And it can be solved by the finite difference method with the boundary conditions of constant heat flux in one surface and insulation in the other. And in order to reproduce a real experiment, we have added some uncertainty to the numerical solution, close to the uncertainty of a thermocouple. And then, to estimate the properties, we define an objective function, which is given by the square difference of the experimental temperatures that we have simulated and the numerical temperatures that we have calculated through the finite difference method. And in order to regularize our results, this function is defined within a small domain of future times, in which the thermal properties are considered to be constants. And this function can also be written as a product of the difference of the vectors, where the numerical temperature is a function of a vector composed by the thermal properties of the materials. And our thermal properties can be separated in two terms. The first one represents our initial guess for the property, and the second one is the increment that added to this initial guess will provide us the optimal thermal property for that time step. So in order to obtain this increment, we need to rewrite our numerical temperature into a Taylor series expansion and replace the gradient coefficients by its matrix form, which we call the sensitivity matrix. And then, if we reapply these values in the original objective function and force its derivative to zero, we can obtain the increment that added to our initial guess will provide the properties that minimize the function in that time step. So for each time step, we need to define a convergence criterion and an initial value for the properties. And then we calculate the temperature and the sensitivity matrix with that property. And with those values, we can obtain our increment. If we achieve our convergence criterion, we can go to another time step. And if not, we add the increment to the initial value and repeat this process. But even before applying the method, there are some details that we need to think about and some analysis that we need to do. And the most important one is the sensitivity analysis, represented by the sensitivity coefficients. They are defined as the first derivative of the temperature in relation to the parameter. And in order to be better compared, they are normalized by multiplying the results by the parameter. And through these coefficients, we can define the heat flux intensity, the position of the thermocouples, the duration of the experiment, and many other details about the estimation. And what we're looking for is an arrangement that makes these coefficients as great as possible. And since the greater their magnitude, the better is the estimation. And here we have the results for the experiment that we have simulated. And the red curve represent the coefficients for the thermal conductivity, and the blue one for the volumetric heat capacity. And the last curve represents the temperature variation. And as we can see, the coefficients for the volumetric heat capacity are proportional to the temperature variation, and the ones for thermal conductivity are proportional to the heat flux intensity. And for this arrangement that we have great sensitivity for both parameters. And even though the magnitude for the heat capacity is greater, the sensitivities don't present dependence on each other. So the estimation can be performed without any major problems. And here, at first place, we have the results for thermal conductivity. And as we can see, the estimated points have a linear tendency, so they can be fitted by a straight line. And the determination coefficients of the linear fit is 0.998, which is really good. And here we have the results for the volumetric heat capacity. But as you can see, the estimated points for volumetric heat capacity have a smaller deviation from the fitted curve, and the determination coefficient is equal to 1. And this behavior can be explained by the sensitivity coefficients. Since they are greater for the volumetric heat capacity, its estimation is less affected by the uncertainty of the experimental data. And for that, they present less residuals. And besides that, as long as we're talking about simulated experiment, we expect that the properties that we obtain through the method are comparable to the ones used in the simulation. And that's what we show here in this table. We compare the coefficients of the curves that we have obtained through the method with the coefficients of the curves from our references. that we used in the simulation. And as we can see, even for thermal conductivity that has a higher deviation, the larger difference observed is less than 1%, which confirms the accuracy of the method. And besides that, the model that we have simulated is very simple and affordable. And so for future work, our main objective is to apply real experimental data in the method. And that's what we've been doing in the last few months. Here we have the curve for the thermal conductivity in a real 304 stainless steel sample. And the experiments performed were exactly like the model described in this work. And we're also working with cemented carbide and another common steels. And of course, these are some previous results that we hope to keep improving, but they confirm the reliability of the method. And besides that, we hope to apply the method for different boundary conditions and even for a three-dimensional model. And so that was our work. And I would like to thank the funding agencies, CAP, CNPq, and FEPMIG for the financial support, my university and Professor Sandro for the opportunity to be here, and also my colleagues from the Heat Transfer Laboratory who have collaborated to the development of this work. And if you have any comments or any doubts about this work, you can contact us or leave your comment below. So thanks for watching.